by equivalent resistance. What's the general formula?
Changing V over
Not for, that's, we can do it that way, sure. All right, so I've got, so the first one, let's say this is R1, say call this R1 and R2. So the current flowing through the top one is just going to be our voltage divided by whatever times R2. The start going through here is the voltage divided by R1. So therefore the current flowing into this was just the sum of those two. This is delta V over R1 plus delta V over R2. This is the current coming out of the battery. So I'm gonna call it I sub PS for power supply. And this would be I3 given what we have written over there, and this is I4. To find the equivalent resistance, since that right there is that current right there, so we'd have the voltage minus our current, delta V over R1 plus delta V over R2 times my equivalent resistance equals 0. Delta V's I can just cancel out. I have, or let me distribute first. No, I'm going to bring this over first. So delta V is equal to delta V over R1 plus delta V over R2 times the equivalent resistance. Let's divide by the equivalent resistance, and so I have delta V over R equivalent is equal to delta V over R1 plus delta V over R2. Can I get rid of anything?
delta V.
And so therefore 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. It looks a lot like capacitors in parallel. Sorry, capacitors in series. So resistors in parallel, the equivalent, 1 over the equivalent resistance is equal to the sum of all the individual ones, which contrasted with capacitance, capacitor equivalent in series is the sum of 1 over. So potentially, if you can remember one of the four, you should be able to get the other ones. Because resistors and capacitors are backwards in the parallel series sense. Questions to hear? So we'll have this already. So now, and why don't I use the same numbers? So this was 5 ohms, 3.5 ohms, 8 ohms, 0.5 ohms, 15 ohms. Sorry, that would be 0.75. 0.75 ohms, and that one was 1.5 ohms. Very similar to the problem we did at the beginning of class, except that was capacitors. Now we have resistors, and we're going to go through the same process, or similar process, I should say. We will not get the same numeric answer that we had the first time because they add differently. So we go through and identify what we can. I know that this right here is series. That right there, parallel. Well, resistors in series, I can just add those straight up, and so I got my 8 ohm right there. Veering off to the right, I've got my 1.5 ohm. You still need to do that, and then over on the left-hand side, adding those together, this becomes 8.5 ohms. Going slightly better. This one right here, I have 1 over 0.75 plus 1 over 15 is 1 over the equivalent resistance. Let's put this right here. So that's 4/3 plus 1/15. Let's see, so 5, so this is 21/15. So my equivalent resistance is 15/21, which is 5/7. So 0.714285.
C.
And so now let's just, like we did before, let's just add these together and then we'll have 3 in parallel. So this now reduces to, I still have my 8 in the middle. I have my 8.5 on the left-hand side. And then on the right-hand side, well, the resistors in series, just add them up. So this becomes 2.2142857. And now I've got 3 in parallel. So the total equivalent resistance is 1 over 8.5 plus 1 over 8 plus 1 over that mess. And whatever the answer is, it better be less than the 2.2.
Yeah, 0.694.
694.
2599.
Did you say it? Say it?
Ohms.
Yes, ohms. Yeah, this there was not for more digits, it was for the unit. Though I should have asked Chow for that last one.
No.
Magniflorious. Questions before I ask you a concept question?
How do you spell that? Something?
That symbol? Ohm, O-H-M.
Oh, that's right.
All right, so I take a circuit here. A 12-volt battery, a 3-ohm resistor, and I would have 4 amperes flowing out of the battery.
Doctor, I have a quick question.
Yes.
Where'd the 2.2 come from?
I added those two together.
Okay.
Other questions before I finish the concept question? All right, there's 4 amperes flowing out of here. I'm pretty sure that we've done this already. And now, I take my 3 ohm resistor here, and I attach to it a 4 ohm resistor up here. And now I have 7 amperes flowing out of the battery. So think about what we just did here. We added a resistor and we got more current. How does that make sense? How can you add resistance and get more current? Because it seems like we just reduced resistance by adding a resistor.
Because to get the same amount of current going back into the battery, you have to increase the amount of current going through the 2 resistors.
Yeah, but why does, just the concept question though is, why does adding a resistor reduce the resistance? Not looking for a math reason, looking for just conceptually. Why does that make any sense? Because ultimately, it does make sense.
Yeah, you can kind of look at a resistor like a choke point, if even. So if you have 2 choke points, that's less resistance than there would be with 1 choke point, because then it has 2 different ones to go through instead of just the 1.
Yeah, and that is the way to look at it. Because if you think about in this situation right here, if I have current flowing across the wire here, in some sense, it's like I have an infinite resistor going that path. And now I've actually reduced resistance from infinity to something. In the fire analogy, there are only a certain number of people who can get through that door at once. Let's suppose we opened up a second door. Even if it opened up just a crack so that only the skinniest people can get through it, that's still 1 fewer person to have to go through that door. And we can get people out a lot faster. So we're adding another pathway. That's why the overall resistance drops.
For the right?
Pardon?
For the right or the left one?
For the right or the left? Well, when we added a resistor in parallel to this one, we reduced the overall resistance, giving us more current flowing out of the battery. Which is not necessarily a good thing. I mean, this is going to drain the battery faster. All right, now, light bulbs are just resistors. The classic light bulb is just a resistor. You have a wire inside there, as current flows through it, you're losing potential, and that potential means you're also losing energy from the wire, and that energy goes into radiation and ultimately heat. And so if it's the right type of material, as it gets hotter, it will heat up and glow. So that's the essence of the incandescent light bulb. It's not particularly efficient because the amount of light coming off of it is so small compared to the amount of energy lost. That's, if you touch a light bulb that's been on for a while, it's hot, that's just lost energy. So if I have a light bulb, so I've got these three light bulbs in series, and suppose one of them breaks. What's going to happen?
None of them will work.
Thus, Christmas lights. The design is different, but I don't know if you have any ones left over from your parents' youth or neighbors or something like that, where one light bulb goes out and every light on the tree goes out. That's the series problem. Instead, if you do it in parallel, if one of them breaks, what happens to the other two?
They get
It's still
brighter.
They would actually not get brighter. Not ideally. Because we still have, again, think of the voltage loop. If I do a voltage loop right here, there's still the same amount of current flowing through here. We're still the same, whatever I gain here, I'm gonna lose here. That doesn't, adding another one in parallel doesn't change that. Now, the overall current coming out of the battery is gonna drop. And Janice, you said something, and I apologize,
Oh, I just said that the light would stay on.
the other ones were. All right, and so this is a whole lot nicer in terms of Christmas tree lights. But I think now the trend, at least the most recent ones I bought, and that was however many decades ago, is they'll have the combination, so this goes out, they don't all go out, you just get a small strand that goes out, and it's easier to find.
So if one goes out, it stays the same.
If, in parallel, if one goes out, these two will just stay the same as before. In a nice ideal board example.
Is there a different pathway created in order for the lights to stay on? Like in the example that we just had previously? Or like where the resistance dropped due to the secondary pathway, is that?
Oh, okay, by introducing several of them, you do reduce the overall resistance, which means that you're draining current faster.
Okay.
Yeah, you get a bigger electric bill with this. So it's a matter of how much is trying to find a burnt out bulb worth to you.
Right.
Or you could just go our route and never put up Christmas lights, and then you don't have to worry about it. Store them forever. Questions? Are we done with chapter 20?
What?
Chapter 20.
We did Ohm's law, we did resistivity and resistance, even did a demonstration that came really close to working. It gets into some AC stuff. Then there's the biology stuff, but who cares? I guess I skipped power. We got 4 minutes, 5, somewhere in there, minutes left. Now let's do a pseudo derivation here. A battery. By the way, batteries don't always have to point the same way. But what I want to know is the amount of power it takes in order to light this bulb. Power is just work per time. You spend a certain amount of energy performing a task, the less time it takes, the more power is used. That's all this is. I'm playing fast and loose with some of the symbols here. Work is just energy, and that's just the charge times the voltage. And, well, charge divided by time.
Is it
otherwise known as.
Current.
So the amount of power it takes, or it's either, depends on how you want to look at it. If I have a simple circuit like this is the amount of power it takes to run the current, or this is the power loss from the resistor, depending upon the situation. I know that voltage is just current times resistance, Ohm's law, so this becomes I times IR, which is I squared R. I also know that current, so delta V equals IR. So current is just going to be delta V over R. So I also could have done delta V over R times delta V, which is delta V squared. So I have three equations for power. And so it's either in terms of the battery, it's the power, it's the power that battery is creating, or in terms of resistor, it's the rate at which energy is lost off the resistor. And we have three equations for that. And the last thing that he does in this is alternating current versus direct current. I've sort of made allusions to this several times before. We're not going to do much with AC current right now. Matter of fact, I'm just going to skip the AC stuff for this chapter. We're going to pick up AC later. But DC, direct current. And this is alternating current. And so in the book, when he talks about the RMS value, if I have current that's fluctuating back and forth like this, so if this is my current versus time graph, what would be the average current? If I found the average, so over one cycle, what would be the average amount of current?
0.
Yes. And so obviously that's not a particularly effective way of computing it, because obviously we can have current flowing back and forth and we still get something out of it. It's not like on average the light's not on. And so they came up with something known as the RMS value, which stands for root mean square. You have seen this in some form earlier with the LabQuest 2 when I asked you to tell me what the RMSE is. That's the root mean square error. This is just root mean square. And so the way that they do it is you start here and you work your way backwards. First we square it. So we take this sine curve right here and we square it, and so I squared would look like, let's see, I guess capping at 1, would look something like this. Then it finds the average of that, which is not 0, which will be somewhere around here. And then it takes the square root. And so if this is some peak value, so if I have a peak value, I guess officially I said peak, that would be square root of 2 times the RMS value. Now, how do you get square root of 2? What I just gave it to you. It's derived using calculus, so it's beyond the scope of the course. Again, we are going to face that later. Just wanted to expose you to it. And I say we're done with 20. How about Monday we establish when the test and that stuff's due? Or not test, sorry. When the quiz for chapter 20 is, we'll do that on Monday.
But quiz on chapter 19 is on Monday, right?
Yeah, quiz for chapter 19 is on Monday. Master set is due a week from today. And test 1A is Tuesday wrong class, is Wednesday, the 19th.
So that was the end of 20?
Sorry, say it again?
That was the end of 20 or that's 21?
This is the end of 20.